today we're going to prove finally. I think it's been a long time coming. The Cauchy theorem, right, which is one of the most important theorems in complex analysis, even if it might not feel like it as we're proving it. And we'll see that this theorem with some massaging will actually imply lots and lots of amazing things in complex analysis. In particular, is at the end of the day what's going to prove, for example, the fundamental theorem of algebra, right? Which, if you think back at what we've done in this class, it feels like we've done very little algebra, right? Mostly we've done analysis. But actually, with the theorem we're going to prove today, and sort of implications of it and extensions of it and so on, we're actually going to prove the fundamental theorem of algebra, which feels like a completely algebraic statement. And so far, all we've done is analysis, maybe a little topology too. Okay, so if you want to, if you have in mind, when is it that we're going to actually say something about algebra and not just do derivatives and analysis the whole time, pay attention, because it's about to happen. It won't be yet this lecture, but this is sort of the start when that's all going to happen. Okay, so we saw that if f from a region, right? So a region, I think of it as an open set and connected, right, over the complex numbers. A function going to the complex numbers is analytic, right? And it has a derivative. Let's say, okay, it just needs to be continued. But let's say that is an. Yeah, I don't need it to be analytic, so let's not go into that. So S is continuous and has a primitive. Then, right, if it has a primitive in omega, then the integral of f over a closed curve, complex path integral, is 0 for all complex closed curves in omega. Okay, right, so we saw this, right? We saw that this meant that fz dz was an exact differential in that definition of exact differential, and basically as you integrate over the path, you get something like the fundamental theorem of calculus. And with this, you get that sort of the integral is the endpoint, the primitive at the endpoint minus the primitive at the starting point. If something is closed and those points are the same, of course, this is 0, right? So, I mean, we worked a little hard to get this, but now we can think of it actually quite intuitively. Okay, and we saw that, right? We saw things like this. If n is bigger or equal than 0, then this immediately gets us that, right? So let's say that this is a closed curve throughout, so that I don't have to write that over and over again, right? The integral of, say, z minus a to the n dz was 0, right? Because it has a primitive. Just take z minus a to the n plus 1 over n plus 1. Moreover, we saw that if, right, n is smaller than minus 1 and the curve doesn't go through a, right? A is not in the curve, right? Because if it's in the curve, then we have issues, right? Because we don't want to be dividing by 0. Then the integral to the path of z minus a to the n dz is also 0, right? Because this has a primitive, right? This function has a primitive in omega except for a. Okay, and if a is not in the curve, then we're all good. Okay, but then something interesting happens for n minus equal to minus 1, and this is where we were. This is where we ended last week. All right, so if we take n to be minus 1, right, then we're asking what happens to integrals of, say, 1 over z minus a dz. Right? And the problem here is that this function, right, if you think of the primitive of this, right, the issue is that log, right, there's an issue. which is just log of z minus a, which would be the primitive of 1 over za, is not single valued. Right? And so the problem is not just at a, but even if we integrate a curve that doesn't go through a, we might get into issues, right? Because if it's not single valued, now being completely high level and intuitive, it could be that this story of the fundamental theorem of calculus, the value you take, when you get the primitive and you take at the end minus the beginning, it could be that you're in different branches and doesn't need to be necessarily the same, even if you're in the same point. Okay, what I said doesn't have to make quite much mathematical sense yet, but I want you to think intuitively about this from now, but this is sort of the issue that can arise. But let's do a calculation. Let's integrate over a circle around A with radius r. Okay, so let's take a circle, right? This is going to be the circle of the point z in the complex plane, such that z minus a is equal to r. Okay, so this is definitely a closed curve, for sure. I mean, we have to say in which order we integrate, right? Because otherwise it's not quite well defined. So we integrate counterclockwise, but it'll be clear when we parameterize. Right, it's a closed curve, and also A is not in the circle, right? A is in the interior of the circle, but not in the circle.